Swayam Prabha. Digital India. Educated India.
Now, let us make a few other observations here. I just said that an optimal solution is this, lambda I star equals 1 and all the other lambdas equal to 0. Are there other optimal solutions? Are there other optimal solutions? Yeah, precisely. So, if there could be other optimal solutions. Say for example, here I said, well, x I star is the one that is giving you the least here, least of these, right. X I star was the one that is giving you the least. There could have potentially been another one, right. Say for example, this could also, there could also be another one. Say, let me write it here. Suppose C transpose x I star is equal to also C transpose x I hat, another index, which another extreme point, which happens to have the same objective value as C I star. Then both I could have taken I hat here, and I could have continued with the same argument. I would have got that one as a solution. In fact, in that case I could have done even more. Instead of putting lambda I hat equal to 1 and everything else as 0, okay, what I could have done is this. I could have constructed a solution like this, lambda I equal to 0 for I not equal to I star and I not equal to I hat. So, if it is not I hat or I star, then it is 0, and the remaining two, the other two, that means I star and I hat, are chosen to be greater than equal to 0 and sum to 1. All that matters is that they sum to 1, because then in that case, if you look at this, this term here, all the, what is this going to reduce to? In that case, if you look at the objective is going to reduce when you look at this summation lambda I C transpose x I, this, because all the other lambdas are 0, what is left is just lambda I star C transpose x I star plus lambda I hat C transpose x I hat, right. But then C transpose x I star is equal to C transpose x I hat. They are both extreme points have the same value. So, then what you are left with is just lambda I star plus lambda I hat times C transpose x I star, and so long as this sums to 1, I still get the same value, right. So, what this means is, if I not only is x I star as an optimal solution, x I hat is also an optimal solution, and the segment joining them, right, the segment joining them, which is lambda I star x I star plus lambda I hat x I hat, where lambda is sum to 1, that entire segment joining them is also an optimal solution. Take any point on that segment, that is an optimal solution, right. So, that is seen in this figure that I had drawn here. You have, this is like your point x I star, this is your point x I hat, and this is the entire segment joining these 2 points. Yeah. So, good question. So, is it possible? So, the question he is asking me, let me draw a new, open a new diagram here, which is a very nice question. So, the question he is asking me is, suppose let us take this sort of polyhedron. Here, suppose your x I star, and the other point that I, so the way I illustrated this was I said let us take this as x I hat, right, x I hat here and x I star here, and these two were both optimal and the entire segment joining them was optimal. But what the question that's been asked is, what if you didn't have this as x I hat, but rather say this as x I hat, say it was what he said was diagonally across. Say suppose this is x I hat. In that case, this would the segment joining them, which is passing through this, would that be optimal? So then where is the fallacy? You are saying it cannot be optimal, then where is the fallacy? The point here is that it will never happen that these 2 points are both optimal, because the very fact that these 2 points are optimal means that they are on the same contour, and then your contour can be moved this way or this way to get a better answer, better value, right. That sort of thing cannot happen. Right. So eventually it has to be that the extreme points are they are on the same face of the polyhedron. Okay. The extreme points that are all optimal are on the same face, in which case the entire face becomes optimal. Yes, yes. So we are exploiting to the hilt here that the problem is linear, okay, in the sense that the objective is linear, the constraints are linear, the shape of the polyhedron, all of that is being exploited completely. Okay. If I had some other nonlinear objective, then a lot of these arguments will not go through as elegantly as they go through here. And of course, if you didn't have a polyhedron, then you don't have Minkowski-Weil theorem to begin with. So that's another problem. Okay, so this says that. So let me come back to what I was saying. So this just tells us that there is at least one extreme point that is a solution. Doesn't mean that there are non-extreme points cannot be solutions. Okay, there can be. That depends on the object. Okay. Now let me ask you: can there be a ray of solutions? So of course, there can be a segment when you have two extreme points that are a solution. The entire segment joining them is a solution. But can you have an entire ray? Means that a point and a direction along which you keep going, and you keep getting all those points are solutions. Is that possible? Yes. So it needs a polyhedron to begin with. For you to have a ray of solutions, you need to have a ray of visible points, right? So the polyhedron has to be unbounded. Okay. So it's interesting to ask this question only if you have an unbounded polyhedron, which means that you are in the regime where all these D's are the Di's are not 0. Okay, there is at least one non-zero Di here. Okay, a non-trivial extreme ray. Okay, then in that case, but does that ensure that you have a ray of solutions? It can be, and then what must be the case for that situation? Right. So remember, we said that we argued that C transpose Di's have to be greater than equal to 0, right? And therefore, we said we should put all the coefficients mu corresponding to it as 0. All the mu's were set as 0. But what if one of the C transpose Di's was exactly equal to 0? In that case, the mu would be immaterial. It would not appear in the objective at all, right? So you look at the objective. Sorry, it's here. In that case, the mu would drop out because C transpose Di is equal to 0, right? So if you have if C transpose Di is equal to 0 for some I, then what can I take the mu corresponding to that I as? I can take it as anything, right? So then the mu I greater than or equal to 0 is optimal. Any mu greater than or equal to 0 is okay, right? Which means then I can start with any solution. So if x star is a solution, then I know that x star plus mu Di belongs to P. This is feasible, it belongs to P, because after all Di is an extreme ray. right. So, I can keep going along di form x star and remain in P. So, x star plus mu di is in P, and what is the objective at x star plus mu di? Well, the objective is C transpose x star plus mu di is equal to C transpose x star plus mu times C transpose di. And what is C transpose di? C transpose di is 0, right. So, this means this is equal to C transpose x star. So, what this means is if x star is a solution and di is a direction such that C transpose di is equal to 0, then x star plus mu di is also a solution for any mu greater than or equal to 0, right. So, I can keep adding this mu di to my point x star and I will keep generating a solution. So, it is not just x star that is a solution, the entire ray starting from x star going all the way along the direction, all the way till infinity along the direction di, that entire thing is a solution. Okay. So, this way you can get a ray of solutions also, right. So, but remember it requires a fine coincidence, your C transpose di has to be exactly 0, right. So, they have, so your objective function, the direction in which it's decreasing has to be exactly orthogonal to the direction in which the set receives. Okay. So, you get a ray of solutions, but remember still that the optimal value is still finite, because the optimal value is not changing because of this orthogonality between C and di. The optimal value just does not change as you go along that ray. That is what this means, right. Okay. So, what has this taught us? What this has taught us is, see, Minkowski-Weyl theorem is super powerful. If you, it basically has reduced optimization over linear optimization, linear programming, to just a matter of enumerating C transpose xi's over the extreme points, right. But so, but the catch in all of this is that we may not know what the extreme points are. To given the Ax less than equal to b type of representation of your polyhedron, your half space representation. From there, finding the corresponding x1 till xk and the d1 till dm, that is where the challenge is, right. And that is what, so the all algorithm design would have to in some way or the other deal with this issue, okay, trying to get to this. Okay, at least if it is aiming to find an extreme point solution, it has to somehow has to get to this issue. Okay. So, this is the qualitative theory of linear programming. Let us, since we have a few minutes, let us just do a few examples. Okay, before I do an example, let me, I want to also mention one more point. Yeah, this is important. Go back to the statement of the theorem again. So, we saw how we made use of this point, that the optimal value of the LP is finite. We made use of this point, that the optimal value of the LP is finite. That is how we got that the mu's should be 0, right. Where did we use that the polyhedron must have at least one extreme point? Yes, we use that in invoking Minkowski-Weyl theorem, right. In Minkowski-Weyl theorem also requires that this set has at least one extreme point. That is when you can write it in this sort of form, right. So, the Minkowski-Weyl theorem, we used it in Minkowski-Weyl theorem. Now, can you give me an example of a polyhedron that does not have an extreme point? Yeah. So, if I take any hyperplane, for example, that is a polyhedron that has no extreme points, right. So, in that case, we cannot say that the extreme point is a solution. Okay. Now, what the, so come back also now to what I had done in the previous lecture, which we said we start with a problem like this, which is simply x belongs to some polyhedron, which means it is written in this sort of form, x minimize C transpose x subject to Ax less than equal to b. But then we converted it to this sort of problem. We said minimizing C transpose x subject to Ax equal to b and x greater than equal to 0. Right? We converted it into this form, remember. So, again emphasis is on form. These A's are not necessarily equal, the B's are not necessarily the same, the C's are also not necessarily the same. In fact, the X's are also possibly changed. Just that it means that there is you can write this in this form and recover back the solution of your original. All right. Okay. Now, focusing on this form again. Now, a polyhedron like this, when I write it as Ax less than equal to b, this sort of polyhedron need not have an extreme point. Right. So, this could be, for example, just a hyperplane, two opposing inequalities that will define a hyperplane that has no extreme point. What about this sort of polyhedron? What about the polyhedron on the right? So, let me be more specific here. We said that A is full row rank, and we said that B can be taken as greater than equal to 0. So, this sort of polyhedron now is a polyhedron which expressed in this form Ax equal to b and x greater than equal to 0 for all the constraints, all the variables. Right. This sort of, what can you say about this? Is a much more specific polyhedron, right? It is not a generic polyhedron like the one on the left. The generic polyhedron may not have an extreme point, but what about this specific one? So, it turns out this specific polyhedron actually has an extreme, always has at least one extreme point. Yeah, see, I'll give you a pictorial view of this right now. We can prove it in the next class. See, the way this sort of polyhedron looks, Ax equal to b, x greater than equal to 0, the way this sort of polyhedron looks is your from the 2 raised to n possible orthants of the space Rn, the x greater than equal to 0 is one of the orthants, right. So, the signs of x will distribute the entire space into 2 raised to n possible orthants. X greater than equal to 0 just chops out, brings out one of them. This is suppose that orthant. So, this is just talking of, this is just expressing x greater than equal to 0. What is Ax equal to b? Ax equal to b is the intersection of several hyperplanes in this space, right. So, it is actually a hyperplane, okay, a lower dimensional hyperplane. It is intersection of several hyperplanes. So, it is as you keep taking intersections, you get lower and lower dimensional sort of affine sets. So, it is some affine set Ax equal to b. It is an affine set that is being intersected with the non-negative orthant, this orthant here, right. So, an affine set, remember, is like just a shifted subspace. So, it is so I'll draw it like this. So, this is my Ax equal to b, and Ax equal to b intersected with x greater than equal to 0 is this region. Is basically just this, right, just that part there. Here, because we are in R2, it looks like a segment, but in general it will be some polyhedral set. This sort of set can also be unbounded. Okay, it is possible, for example, it can be that this Ax equal to b is aligned like this with the axis, in which case it will be unbounded in this direction. It can be unbounded, it is not a bounded set. But one thing is for sure, it cannot escape eventually, it cannot happen that it does not hit any of these axes. It will either hit this axis or this axis, one of those n different axes is going to be hit. So, it will intersect one of them, and when it intersects one of those axes, okay, one or more of those axes, right. Okay, this is all happening in higher dimensions. So, remember, when several of its coordinates, when it intersects, several of the coordinates of x will end up being 0 and the others will not be 0. When you get to that sort of point will end up being an extreme point of the set. So, the kind of polyhedra that do not have extreme points are those that are sort of say hyperplanes, etc., which you cannot which you are not able to sort of confine. So, here the x greater than equal to 0 forces you effectively to end up having an extreme point. So, I am giving you an intuitive picture here, but basically what you what's the claim the thing to notice is a set like this, Ax equal to b and x greater than equal to 0, this sort of polyhedron always has an extreme point. So, what this does is this actually helps us in designing algorithms for linear programs implicitly. A set like this, an optimization problem like this, it did not even have an extreme point. So, we could not even say where that we did not even have a target saying okay we are looking for an extreme point to solve the problem. Now, once we reduce it to this standard form, not only is it standard and easy to program and so on, in addition it is guaranteeing us that there is an extreme point. So, the search for a solution also becomes easier. Okay. So, you get this sort of set must have an extreme point. Is this clear? Okay. So, yeah. So, this is so the extreme points of this sort of set are what are called basic feasible solutions. I will talk about this the basic feasible solutions. So, since you have about 10 minutes, I can just define you for you what this is. So, if I take the set the matrix A, okay, and I can now what I can do is I can write it in the following form. So, remember A is full row rank. So, if A has m rows and n columns, then I can write it in this sort of form, where the vectors B are such that they are columns of A that are linearly independent. Okay. And I can how many can I put in how many such columns can I add to B? M of them, right, because that is the rank of A. So, I will take B to have m columns. Okay. So, B will now have m rows and m columns, and all the remaining n minus m I am putting in n. Okay, n minus m columns. So, I can choose such m columns from the n columns that I have for A. Then that will give me a way of writing A in this sort of form as B and n. And then if I solve using this, what I will do is to solve for x, what I will do is I am going to multiply this by x. Let me write this as xb and xn. So, this xb is of length m, it is what multiplies with b, xn multiplies with n, right. So, what I will do is I will solve for xb and put xn as 0. So, putting xn equal to 0 and solving for xb, what does this give me? This gives me the equation bxb equal to small b, right, and because B is now m cross n and it has linearly independent columns, right. So, B is invertible. So, xb will be equal to B inverse B, right. So, a point like this xb comma n equal to B inverse B comma 0, this sort of point is what is called a basic solution. A basic solution is a point like this. So, what you need to do is you look for columns of A that are linearly independent, you will m of them, you should be able to find m of them. So, take m of these linearly independent columns, solve for the x's corresponding to those columns and put all the remaining x's as 0. Okay. So, see, put the remaining x's as 0 and solve for the x's that are corresponding to this column. That will give you a vector like this, b inverse b comma 0. Now, this sort of vector may not satisfy x greater than equal to 0, right. So, if b inverse b is also greater than equal to 0, then we call it a basic feasible solution. So, what I will argue next time is that actually basic feasible solutions are the same as extreme points of this sort of set. So, okay, Ax equal to b and x greater than equal to 0, solving for extreme points is effectively solving for finding points in x by putting some of the coefficients equal to 0 and solving for the rest, right. And that is like what I was saying, you have this affine set, it intersects, it hits one of the axis. By when you say it hits the axis, it means that some of the coordinates become 0, you need the other ones need to be found, and that then gives you the that the other ones need to be found through the equations that you have. Okay. So, that is how we get to extreme point. We will do this in more detail next time.